All right, ladies and gentlemen, how are we doing today? All right, so we are looking at Bohr models, which you should have started looking at when we did our PhET simulation on Tuesday and Wednesday for your e-learning assignment. So if we look at our Bohr models, the first thing we need to notice is that the Bohr models have specific things that we need to know. The first thing we need to know is the orbitals, okay? The orbitals really just mean the different rings on the periodic table, or sorry, the different rings around our atom. Okay, so our atom is going to have rings or orbitals that hold the electrons. The only thing that goes in there is our electrons. Remember that our protons and our neutrons are in our nucleus. And you might remember that from biology. Remember, the nucleus is kind of like the brain of your cell in biology. The nucleus is kind of like the brain of our atom because it tells us which atom we are looking at. All right. And so if we're looking at specific atoms, we can tell based off the nucleus what the element is or what the element's telling us about. Okay. The orbitals are going to be super important when it comes to how many electrons fit in there and how we draw other things later, like our ions, okay? So our first orbital, think of it as the rows of your periodic table that you've just gotten today, okay? If we look at that first row, we have 1, 2 elements in the first row. Think of those elements like your placeholders for your electrons. Our electrons can go 1, 2, and then that whole row is done. So the whole first orbital is done after 2 electrons, okay? Our second row is going to be the second orbital. So 1, 2, 3, 4, 5, 6, 7, and 8. And then our second orbital is done. Our third orbital is going to start out with 1, 2, 3, 4, 5, 6, 7, 8. As long as we're looking at the third ring or the third row. But unfortunately, our third orbital is actually going to have 18 because these wonderful guys can end up in our third orbital, just like our third row. Okay, and that's a little bit more specialized, okay, because our valence electrons, the outermost ring, can only hit a maximum of 8. And so if we put these guys in row 4 with the rest of them, it would turn out to be 18. So these 10 in our middle actually go in the column above when we're talking about our orbitals, all right, when we're talking about where they go. But for the most part, we need to remember that our first orbital can only ever have a maximum of 2. Our second orbital only ever gets a maximum of 3. And our third orbital gets a maximum of 8 if we're talking about the third row. But if we're in the 4th, 5th, or 6th row, all right, it can have 18 in the 4th through 7th row. So again, remember, think orbital as in the row number. Okay. Now, our protons. Our proton number is the easiest one to find because our protons are on the periodic table. Okay. Again, if we look at our periodic table that you should have just gotten today, you can see that there are numbers in the top, usually in the top left or top middle of your periodic table. Those numbers are the number of protons. So we don't have to worry about anything else. Those are just our proton numbers. All right. So we have those numbers that we can use always. Okay. We see the periodic table, that number, always the number of protons. We can see that our proton number changes each time we change elements. No 2 elements have the same number of protons. And we can go all the way from 1 all the way down to the bottom at 118. So 118 right now is our maximum number of protons, okay? So now if we look, okay, the protons come straight from the periodic table. Our electrons should be the same as our protons. And we might have gotten that from our POGL or our FET, but our protons should equal our electrons. And this is almost always the case if the charge is 0. Okay, if our charge is 0, our protons equal our electrons. Okay, they got to be the same because our charge is equal to our protons minus our electrons. So if our charge is 0, our protons should equal our electrons so that they add up to 0. All right. The next thing we need to know is isotopes just mean elements with different masses. So you'll notice on your periodic table, almost all your masses from about 1 to about 92, I believe, are going to have mass numbers with decimal points. Okay, so like hydrogen's 1.008, carbon's 12.01. You're going to see that because hydrogen's got these different isotopes. There are 3 of them. Hydrogen shows up as hydrogen 1, hydrogen 2, and hydrogen 3. Almost all of our hydrogen is going to be hydrogen 1, which is why it's 1.008, because almost all the hydrogen you're going to find is 1. But there are some 2 and 3, and that's when we get more into stars than anything else. So our stars have hydrogens called deuterium and tritium, which are hydrogen 2 and hydrogen 3, which cause different reactions to happen. And that's a little bit smaller of an amount, which is why we don't see a lot of it. Right? Isotopes mean same element with different mass. Okay, so now we have different masses for our elements, which are these numbers right here. Those mass numbers are just the numbers to the side, right? Those are the specific masses we're talking about when we say different masses. So like if you look on your periodic table, your beryllium should be something like 9, but ours is 8 in this case because sometimes beryllium comes in as 8. Neon is almost always 20. So it's usually closer to 20, but it can be 21, all right? And so we need to know that when we're finding our mass number is equal to our protons plus our neutrons, which is something you might have come up with on your FET again, right? So that should have come from there. So we can go the opposite way, and we can take our neutrons are going to be equal to our mass number minus our protons. Okay, and again, your mass number is that number on the bottom of your periodic table. So if we go back to our periodic table real quick, okay, your mass numbers are these guys down here, okay? And they might be a little bit different than mine, but they're on your periodic table right there, okay? So we can round those numbers to the nearest whole if it doesn't give you a mass number already. Okay, but for these ones, beryllium, I gave you a mass number of 8 in this case. Okay, so the first thing I want us to do is to think about those 3 subatomic particles. So I'm going to write mine out, my protons, my neutrons, and my electrons. Okay, I need to know how many of each I have. So if I look at beryllium, beryllium is our 4th element on the periodic table, so it's got 4 protons. This beryllium is the mass 8. So if I take my 8 minus my 4, I'm going to get 4 neutrons. And because our charge is 0 for anything that doesn't tell us, so all of these have a charge of 0, I have 4 electrons. So I have 4 of everything. So to draw it, I'm going to do 2 things. I'm going to draw my nucleus, okay? And you guys were doing your nucleus, right? You saw that in the FET, it would show little balls like flying in, right? The red ones and the gray ones. We can draw those too. That's awesome. But I'm going to tell you right now, I personally would never in my life draw 118 circles for protons and then another probably 140, 150 for neutrons. That's way too much drawing for me. So instead, I'm going to draw a little box. And my box is going to be my nucleus. And in my box, I'm going to put my 4 protons. I'm going to write 4p and my 4 neutrons. I'm going to write 4n. So I got 4 of each. Okay. That's good enough for me. So that's probably good enough for you too. And then what I'm going to do is I'm going to draw my electrons. Okay. Beryllium is in the second row. So I know how many rings am I going to need. If it's in the second row, I'm going to need 2 rings. So I'm going to draw both those rings. 1, as you can see, I'm a great drawer. And 2. And so I need 4 electrons. Our first orbital, we wrote down, can have a maximum of 2 electrons. So we're going to put 1, 2. And then our second orbital can have 2 more. So I'm going to go 1 on top and 1 on the side. Remember, these ones aren't specific spaces you have to go, but it might be helpful to start the same way we're going to follow along in the future with other models we draw. Okay, but if yours looks a little bit different, your electrons are in a different place, that's totally fine. Okay, so I'm going to do that again for phosphorus. Okay, so I'm going to start with phosphorus now. And I have my protons, my neutrons, and my electrons. Again, phosphorus is number 15 on the periodic table, which means it's going to have 15 protons. Sorry, which means if it has 15 protons, we know for a fact which other one? We know if there's no charge, we have 15 protons, we have to have 15 electrons. All right, our neutrons is where it gets a little bit different. Remember, our neutrons is where we subtract. On your periodic table, it should say something along the lines of 30.97, but this one says 33. So we're going to do 33 minus our 15 to give us, what is that? 18 neutrons. Now, phosphorus is in our third row. So the first thing we got to draw again is our nucleus. So we draw our box. In our nucleus, we're going to put our protons and our neutrons. And then we get to draw our rings, and we need 3 rings because it's in the third row. So we have put 2 electrons in our first row. Our second row is where we're going to put our 8. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. And then our last row is going to have our last remaining 5. So we go 1, 2, 3, 4, 5. And I'm going to let you do neon on your own, but I do want to mention something real quick. Okay, right here. There are some electrons that are more important than others. Okay, our electrons that are more important are the ones that we're going to use to make different compounds of elements. Because think about things like water is a compound of multiple elements, right? And so that means some electrons are going to be used up to combine to make those different compounds. Something like salt. Salt is one of my favorite ones to think about because sodium by itself is actually going to explode in water. And if you know anything about your own body, your body is made up of 70% water, which means if we ingested sodium, sodium would make us explode, right? We'd explode because we're made of 70% water. It explodes in water. Okay, that's crazy. Chlorine. Chlorine is a gas by itself, and the Nazis used chlorine gas in World War II at their concentration camps. That's what they used to kill people, right? So Nazis were killing people with chlorine gas. Sodium explodes in contact with water. Those two things are super, super dangerous for us. But if we combine those two, we make salt, table salt. You eat it every day. So there's some parts of our atoms that need to combine with other things. And so those parts are called our valence electrons, all right? And our valence electrons are the outermost orbital. electrons. Okay, so the electrons on the outer ring. So if we look at beryllium, if we count our valence electrons, beryllium's got 1, 2 valence electrons. Because those are the only ones in the outer ring. The ones closer to the middle, those ones are being pulled by the nucleus. Those ones aren't going away. It's a full ring, and that element does not want to lose full rings. It's okay losing those extra 2 because that whole ring, they need 8 of them to be full. But if it's only got 2, those 2 aren't being used, so we don't really care about them. It's okay if they go away. Same thing with phosphorus. Phosphorus has 1, 2, 3, 4, 5 valence electrons because those are the only ones on the outer ring. So valence electrons equals 5 because it again needs 8 for that ring to be full. But this time it's got 5, so it's easier to try and find a couple more to bring in than it is to try and lose 5 of them because those electrons have to go somewhere. We aren't magic. Electrons don't just appear and disappear. They have to be from different elements. So we're sharing them, we're giving them away, we're taking them from other places. It's not just a disappear and reappear. It's not a magic act. It's actually sharing. All right. So those electrons are going to be our most important electrons. Those are the ones we always got to think about. All right. And when we think about those in terms of our ions. So ions are actually going to be our charge of our element. So this is our charge, atoms with a charge. We have 2 types of ions. We have cations. And think of cations as they got that big T in there, right? So those are cations are the positive charges because cats have pos or positive charges. Anions are going to be the opposite. Anions, think of anions as a negative ion, right? We just broke apart that word. It's a negative ion. So these ones are the minus signs. Okay, so if we were to draw some of these, let's look at 2 of them. Okay, so let's look at our sodium, which is element number 11 on the periodic table. So it initially has 11 protons. And it's got neutrons. If we looked on the periodic table, the mass number is 22.99, which of course we know if we round that, it doesn't go 22. That one rounds all the way up to 23. So it goes to 23 here. So then if we take our 23 minus 11, we end up with 12 neutrons. And now our electrons. This is always the hardest part. So let's actually start by drawing it with its 11 electrons that we had originally, okay? So if we draw our nucleus, we have our nucleus, which is I'm going to draw as a square with 11p and 12n. Sodium's in our 3rd row, so it gets 3 rings on the period on our or 3 orbitals. Okay, so 1, 2, and 3. Okay, so I'm going to put my first 2 electrons on the first ring. And then it's full. My second ring can have up to 8. So then 1, 2, 3, 4, 5, 6, 7, 8. Remember, originally our electrons should be 11, which means we need 1 more on our 3rd ring. But because we have a positive 1 charge, positive charges means that we lost an electron because we have a charge equal to protons minus electrons. If we have a positive 1 charge, that means we have a plus 1 equals 11 protons minus some amount of electrons. So if I add my electrons to the other side and I subtract my 1 from both sides, this crosses out, and I get my electrons equals 11. Oh, sorry, plus or minus 1. And 11 minus 1 is 10. So that means we lost an electron. So we lost a negative charge, which means we can actually erase this whole ring. And we're left here with some brackets around here and a positive 1. Okay, so we lost an electron. Okay. Which means a negative charge means we gained an electron. That's right. All right, so originally, let's do this one again. So fluorine protons equals 9. Neutrons, our mass number for this one is 19.00, so it's already 19, which means our neutrons, we have 10, because 19 minus 9 is 10. And our electrons, we have 9 originally. All right, so if we draw this one, we have our nucleus. Good enough. And we have our 9 protons and our 10 neutrons. And it's in the second row, so we need 2 rings. And originally, fluorine has 1, 2, 3, 4. Sorry, I forgot the first 2. Silly me. So 1, 2 in the first ring. Then we go to our second ring. We get 1, 2, 3, 4, 5, 6, 7. But because it's got a negative 1 charge, got that minus 1 charge, that means we need 1 more electron. So we have to add 1 to give us 10, which means we have to put another electron on there. So now what we notice is that sodium has a full ring when it lost 1 electron. Fluorine, when it gained 1 electron, it has a full ring. So the goal with those charges is for everybody to have a full ring, to be happy, to have a full valence shell. So our goal is to have a full valence shell. Right? And so that's the goal anytime we have ions. And that means we gave electrons away or we took electrons. So let's think about this in terms of sodium and fluorine, right? If sodium had 1 electron it gave away, we can imagine that that 1 electron it gave away, right? That missing electron just moved down and was given to fluorine. And so that's how we both became happy. That electron had to go somewhere, so it gave the electron to fluorine, and now we have something called a compound that's going to be a combination of 2 different elements together, held together by those charges. And again, we can't forget about the charge, so just like before, we got to put our brackets around here, and it becomes a -1 for its charge. If you have any questions, just let me know. Otherwise, have a good rest of your day. Finish up this worksheet for me.